All right, so after learning how to simplify a rational expression, and hopefully you've had some good amount of times practicing on that specific skill right there, let's now move on to learning how to multiply and divide rational expressions. So let me start out with multiplying the rational expressions. All right, so for multiplying rational expression, before we really get into doing that, allow me to introduce a very familiar problem to anyone. So here we are at problem number 1 right here. I would like to demonstrate that very familiar problem to anyone. The instruction here says, let's multiply these two fractions. And so the dot here is a product. It's indicating we got a 4 out of 25 or 4/25 multiply with 5/8. We don't have to wait until a college course in algebra to be able to multiply these two fractions. They start teaching multiplying fractions since 5th grade, 6th grade. Okay, so what's the idea of doing this? Anytime we're multiplying two fractions, we just simply multiplying numerator with numerator, denominator with denominator. So that's it. So 4 times 5 is a 20. 25 times 8 is a 200. Now we have come to the final fraction. So again, the fundamental here is anytime multiplying two fractions, we're multiplying numerator with numerator, denominator with denominator, and that's how we come up with the final fraction. But now, and I could have mentioned, and I should have mentioned this, the multiplication here can be done regardless we have reduced, whether or not we have reduced any one of these two fractions. So we can just always get straight into doing the multiplication. And then now at this final fraction right here, let's think about reducing it. This is where simplification comes in right here. And so that reduces down to 1/10. And allow me to skip the little steps here. Of course, we have to write 20 into product of prime factors and 200 into product of prime factors and all of that. And then after canceling out all of those, we arrive at 1/10. So the fundamental is here. Multiplying numerator with numerator, denominator with denominator. And so now allow me to remind one fundamental to anyone in terms of multiplying any two fractions. Anytime we have a fraction p over q, and multiplying that with another fraction, let's say some r over s, the final fraction can simply be found by simply multiplying p with r multiply together to become our final numerator, and p and q times s multiply together to become our final denominator. And this is the fundamental in terms of how we can multiply any two fractions. And of course here I'm limited in board space, so allow me to skip these conditions, but textbooks will always remind you that hey, q has to be a non-zero and s has to be also a non-zero, and then all of that. So neither one of q and s can be 0. And so now this is the fundamental. All right, so now we're at this demonstration problem number 2 right here. We are instructed to multiply two rational expressions. So I've had this recommendation from the earlier lessons, and now I want to emphasize it again. Anytime working with rational expression, think as closely as you can to working with fractions. So there's one rational expression. Think of that as one fraction. There's one more. There's another rational expression here. Think of that as another fraction. These two are multiplied together. So that's what we're instructed to do. We are instructed to multiply the two rational expressions here together. So as I keep yelling out loud, think as closely as you can with working with fractions. Then wait a minute. Can we actually bring in that same philosophy, that same fundamental of how we multiply two fractions into doing this? And the truth is, yes, you can do the exact same way. So meaning, now I can just simply And currently regardless whether I have completely factored any one of these or not, and regardless whether I have simplified any one of these the rational expressions, that's not important, but the fundamental is here. To multiply these two rational expressions. Now think of the P over Q. P is one entire polynomial, Q is another entire polynomial, so P over Q is one rational expression. Multiplying that with another rational expression, this same method works the same. This same philosophy, this same fundamental is going to be applied the same way. So we multiply the two numerators together to get some final numerator. We multiply the two denominators together to get some final denominators, and the rational expression comes out exactly in the same order. So now in that way right here, proceeding into this, applying that fundamental into this problem right here, here's how I'm seeing it. The entire numerator x squared plus 4x plus 3 multiplied with the other x. Let's keep it like this. The final numerator will become something like this. The final numerator comes from multiplying x squared plus 4x plus 3. That's one numerator. We're multiplying with the other one. So this expression represents the final numerator. The final numerator of our final rational expression. And then, proceeding in the same way right here, the denominator of our final rational expression comes out from multiplying the x squared plus 5x plus 6 with the other x plus 1 all squared. So I'm going to write it like this. Yes, ladies and gentlemen, that's how simple it is to multiply any two rational expressions. We just multiply numerator with numerator, denominator with denominator. And first thing right out of the box, let's keep it that way, in factor product form. But now at this point, we definitely want to simplify this final rational expression. And that's where, again, your skill that you have learned previously about how you can factor each one of these little polynomial expressions can be useful and can be brought into here. Now we have already had some factor product right here. We got, that's one factor and that's another factor in the entire bigger product. This is one factor and this is another factor right here in an entire bigger product. But we want to find out whether we can factor out that part right here where I underline with a squiggling line, and then factor out this part right there. And that's why you've had, I'm pretty sure you've had that lesson earlier about how you can completely factor. So I'm now going to go ahead and factor out the x squared plus 4x plus 3. And then of course the entire x squared plus 4x plus 3 is still in product with x. So the x is already one existing factor that we found. But let's go ahead and factor out this x squared plus 4x plus 3. So in my next step, x squared plus 4x plus 3 can be rewritten as x plus 3 times x plus 1. And don't forget, we still have that other factor x that came out from the earlier step. Now I have completely factored the numerator. I'm going to do the same for this x squared plus 5x plus 6 in my denominator. So factoring that out, it's going to give me x plus 3 times x plus 5. That's the complete factor of the x squared plus 5x plus 6. But don't forget, we also have that x plus 1 all squared. So x plus 1 all squared. So now we have completely factored numerator and denominator. So in that case right here, now we're going to start simplifying our rational expression. So now treating this as a rational expression, that has already been put in product of prime factors for both numerator and denominator. We apply our skills from the previous lesson. Common factor x plus 3 can get cancelled out. It gets cancelled out. X is not common with x plus 5 and x is not common with anything else. X plus 1 is common with one of the x plus 1 down here. So we can cancel that away, and then that will leave behind for me a factor x plus 1. So now let's put it all together. The final simplified expression here comes to, in the numerator, there's only, after canceling out these two factors, we only have one factor, x, left. So that's x over, now we have x plus 5 remains in the denominator and another factor, x plus 1, that remains. So now we're looking at x plus 5 times x plus 1. So this is our simplified expression. So we multiply, and then at the end, we always have to simplify. We multiply, and at the end, we have to simplify. Just like the demonstration problem I've done in problem 1 right there. We multiply to get some final fraction, and then at the end, we always have to reduce that fraction. So same exact philosophy, same exact fundamental that goes into multiplying any two rational expression. We multiply first, regardless each one of the two parties here are in reduced form or not, or in simplified forms or not. Just go ahead and multiply them, and then after we multiply, we're gonna recognize the common factor. We factor completely top and bottom, and we're gonna cancel out and to simplify. So I've shown throughout problem 2 the fundamental of how we can multiply any two rational expressions. But then believe me, this work has been done for centuries, and as it has been done for so long by many generations of people, it gets evolved. The methods it gets evolved. So in these days here, instructors tend to teach their students the following. Let's say I'm going to roll back to the problem a little bit. Originally, x squared plus 4x plus 3 over x squared plus 5x plus 6. And we multiply with x over x plus 1 all squared. Instructors in these days, because the idea it all came out from, they realized that, hey, instead of completely factoring way at the end like this, it may be a little too gigantic and confusing. And so people over generations have come to a more sort of like a more revised way of doing it, So I'm just talking about a revision, sort of like a slightly different route, a slightly different order of the work right here. So what I have done in the demonstration was I just simply multiply regardless of simplifying or not. But so after generations of mathematicians working and teachers working on these, and they teaching it down to the students, they come to the following order of the work. They're going to say, hey, why don't we just completely factor each one of these? So the first rational expression, let's completely factor it. So x squared plus 4x plus 3 before multiplying can be completely factored into x plus 3 times x plus 1. And then let's also completely factor the denominators. So the first denominator here is completely factored as x plus 3 times x plus 2. So that's how I have completely factored the first expression in terms of numerator and denominator. And let's do the same. And this, for the other rational expression, it was already gladly in complete factor form. So let's just rewrite it. X over x plus 1 all squared. So now I'm saying that this is the evolution that I was talking about right here. So over time, after centuries and generations of people doing the same work right here, instructors now in these days tend to tell the students, let's go ahead and as the order of the work, let's first factor out completely all of the rational expressions you've had for numerator and denominators. And then after that, you have put all of your rational expressions in complete factor form. Now we're going to start multiplying. And so the multiplication comes in. And so that same fundamental of multiplication comes in. All we do is just simply bring all of the factors together. So x plus 3, x plus 1, and then there's x. And then now in the denominator, we have x plus 3 times x plus 2 and times x plus 1 all squared. So the multiplication still stays exactly with the same fundamental we have learned. It's just in this way of revising the work right here, we have done completely factoring fast. Take all of our the rational expression into complete factor form. But I'm not talking about simplification. We don't have to simplify. We just completely factor out all numerators and all denominators, and then we multiply. And now, since everything is already in easy factor form right here, we can just easily look for common factors and start canceling out the common factors. And so, of course, the final answer here is going to arrive at the answer that we have already found. All right. So in that way, we have come to a finalized solid method for how to multiply rational expressions. And here I'm simply using a plural here, indicating that we can use this exact same method for multiplying even more than 2 rational expressions. So first step, we're just simply going to factor each numerator and denominator completely. And this is exactly reflecting what I was doing in the revised work of my problem number 2 on the board earlier. And then we multiply the numerators and the denominators. And this is the way how we actually, this step 2 right here is the fundamental of how we multiply any 2 rational expressions. And then the third step here is to simplify by dividing out the common factors. This is the steps where we simplify our final multiplied rational expression. All right, so after learning the solid method of how we can multiply any 2 rational expressions, let's bring that solid method into solving a problem where in this example 1, we're instructed to multiply these 2 rational expressions. All right, and so I just now put the instruction steps on the corner of the board right there. So first step, as you can see, let's go ahead and completely factor all numerators. So in this problem, we have 2 rational expressions. So this is one numerator. This is another numerator. So the first step is to completely factor all of the numerators. So the first numerator here can be factored into x times x minus 4. And once again, you can always refer back to the lessons where I show how to completely factor so that you can see the reason why I have arrived at something like this for x squared minus 4x. So that's how I have completely factored the first numerator. The next numerator right here, it looks like that's all we can have. It's already one factor on its own. The first denominator here is going to be completely factored as x plus 3 times x plus 2. That's how I have completely factored this first denominator. And then the other denominator here is already by its own, on its own, one factor. And so now this is already at the end of step 1, where we have completely factored all numerators and denominators. So now the next step is to multiply. So now we have one rational expression in complete factor form, and we have another rational expression in complete factor form. So let's go ahead and multiply them. And so multiplying them here means just this gigantic numerator is to be multiplied with the other numerator, making it x in product with x minus 4 in product with another factor x plus 2. And multiplying the 2 denominators here is simply going to give it x plus 3 times x plus 2 as 2 factors, but multiplied with another factor x. That's how we can multiply 2 rational expressions together. And this is the end of step 2. And so now at this point right here, I have recognized x and x is a common factor. That will get canceled away or being divided away. The x plus 2 and the other x plus 2 here is another common factor that can be divided away. And so now in this entire final rational expression, after canceling out, after dividing away the common factors, then we have only these remaining factors. In the numerator, we have x minus 4 as the remaining factor. And in the denominator, we have x plus 3. And that's how I have multiplied. So we multiply and we simplify. And that's how I have multiplied these 2 rational expressions. And that's my final rational expression. All right, and so now we are ready for getting into dividing any 2 rational expressions. Okay, so a couple reminders. So now this one fundamental we have known since long ago. That's, back in the days we were dividing fractions. So if you have a fraction, P over Q, and we're dividing that fraction by another fraction, R over S. So dividing P over Q by R over S right here. The actual way of doing that, and it has been the way, the actual way of doing that is to rewrite this division problem as a product of P over Q, but multiply with the reciprocal of R over S. So the reciprocal, making it becomes S over R. And so now turning the fraction R over S into S over R right here. This is what we call the reciprocal. So R with S over R here being the reciprocal of R over S, we now just simply performing that usual multiplication problem between these two fractions. So really, in the way how I see it, the work of dividing any two fractions, the work of dividing fraction is exactly the same as can be done just like how we're doing the work of multiplication, except for we take one additional step, rewriting the division as a product. Okay, so as a quick reminder, let's bring up one little problem right here. Let's say we have a 2 over 15, and we want to divide that by 3/5, for example. So this problem right here is so elementary that even an elementary student know how to do. So we rewrite this problem here as a 2 over 15. We keep it the same. We multiply with the reciprocal, the twist over, the flip over. So now we're looking at 5 over 3. And so now we're looking at 10 over 45, and then we're going to start doing our simplification, our reduction after that. So simplifying it or reducing it, it comes down to 2 over 9. And that's our final fraction right there. So that's how we have been doing it, and it's so elementary to the point that I don't even need to formally reteach that. Okay? But so the fundamental is here. The fundamental is here. And so in that way, the idea now is that when we're working with dividing rational expressions, no longer simple fractions like this. Okay? Now we're working with rational expression. Can we bring this exact method, this exact philosophy, this exact fundamental into dividing any two rational expressions? Because rational expressions in the end heavily looks closely to be a fraction. Okay? And so in that way, yes, the truth here is yes, this exact fundamental carries into how we doing a division among two rational expressions. Okay? And so now allow me to bring in a demonstration problem right here. All right, so here we have a problem right here to see how that same fundamental in terms of dividing two fractions can be carried into this problem right here. So here we actually instructed to divide this fraction 3n squared over n squared minus 4n by this other big rational expression right here. So we have a rational expression being divided by another rational expression here. Okay, so as I said earlier, yes, we can carry that same fundamental. So P over Q divided by R over S means we can rewrite that as P over Q. We keep that first rational expression the same. We turn the second rational expression, the one after the division sign, we turn the second one into its reciprocal. And then we perform now a multiplication problem. So in that way, the big step here is that we're going to keep the first rational expression, 3n squared over n squared minus 4n, the same. But for the second rational expression, which is 9n squared minus 45n and all that, we're going to take the reciprocal. So the reciprocal of this rational expression is going to look as following. We now have n squared minus 7n plus 10. And that's going to be over 9n squared minus 45n. But now between these two rational expressions, we're performing a multiplication problem. And so now at this point, all of a sudden we realize it is important that we have learned how to multiply any two rational expressions before this point or prior to this point, because now we can go ahead and utilize the skill we've learned in the earlier lessons, in the earlier part of this video lesson, into this problem right here. So now the usual steps are going to carry out. So according to what we've learned earlier, we're going to go ahead and factor completely each numerator and each denominator. So 3n squared on top is already in its factor form. N squared minus 4n can be factored into n times n minus 4. And again, how do I factor these? If you're anyone feeling a little shaky with how I factor any of these denominator or numerator, make sure you review even the earlier lessons of when we were learning how to factor a polynomial expression. All right, so now multiply. The next numerator here, n squared minus 7n plus 10, is factored into n minus 2 and n minus 5. The denominator here can be factored into 9n in parentheses n minus 5. And so 9n here was a common factor, or the greatest common factor among the two terms here. That's how I simply pull it out. All right, and so now after completely factoring out all numerators and all denominators, now we're going to multiply. And so multiplying two fractions, any two rational expressions, simply just means we're going to multiply numerators with numerators and denominators with denominators. So the final numerator is going to look as following: 3n squared times n minus 2 times n minus 5. That's how, since these are all in factor form, multiplying together, it's just simply, as the way it looks here, we just simply put all the factors together. Now the same way with the denominator here, multiplying the final denominator will be the product of all of these two denominators. And so we have n times n giving it n squared. So my final denominator looks as following: 9n squared, and then we have n minus 4 and n minus 5. All right, and so now with this final fraction right here, with this final rational expression, we are going to simplify by canceling out common factors. So I recognize n minus 5 being a common factor, the n squared is a common factor. And further, I recognize there's a common factor 3. There's 3 here, and there's a factor of 3 that goes into 9 right here. So here I'm going to cancel that 3. Okay, and then the leftover factor in this 9, after canceling the 3 away, that's going to be a 3. And so now our final rational expression, okay, making it equal. So in the numerator, the remaining factor really is just the n minus 2. So now I'm looking at n minus 2, and now divided by, and then in the denominator, the only remaining factors are n minus 4 and 3 right here. So we can write it as a 3, and then in parentheses, n minus 4. Now we have found the final rational expression. So this final rational expression right here is the quotient between this rational expression and the other rational expression, or it's the quotient of that 3n squared over n squared minus 4n divided by this big rational expression. And then optionally you can distribute that 3 right here, and then making it n minus 2 over 3n minus 12. But any one of these two is just your, depending on everyone's preference. Okay, and so problem 3 right here really brought in for us and guarantee that the way we're doing dividing two rational expressions is exactly the way how we've been doing dividing two fractions. Okay, so the fundamental here, the big fundamental here is to rewrite the division problem as a product, as a multiplication problem, where the first fraction, the first rational expression stays the same, and then we're gonna rewrite the second rational expression as its reciprocal, and then take the products between the two. And so, and after that point, everything is exactly a multiplication problem. So that's the way how I'm seeing it. And so throughout this demonstration problem, we have come to a a formal setup instructions right here for how we can divide any two rational expressions. All right, so on my screen here, this is a setup instruction for how we can divide two rational expressions. So the first big important step here is to rewrite the division as the product, as a multiplication of the first rational expression and the reciprocal of the second. All right, so this is one big step, and then now you can see that starting step 2 and to the end, this is mainly how we do a multiplication problem as usual. All right. And so after seeing that finalized, that formal methods being displayed on screen right there, then I have a couple of remarks here for everyone. So something that's worth your attention. So the first remark here I want to point out is that, so think of a division between any two rational expressions. Think of a division as a, right? Think of a division expression. So first remark here, think of a division between any two rational expressions as a multiplication between the first with the reciprocal of the second rational expression. All right. So keeping it that way right here, it's easier to remember the steps. Otherwise, if you're looking at follow through the steps one by one right there, then it's going to take a lot of memory, right? And as we're developing our skills right here, a lot of times we tend to memorize the steps right here once we see a how-to instructions. But now to make it easier, this is how we think about the way how we perform division between any two rational expressions. Remark number 2. Now I have to remind anyone, a fraction from the first day we've learned about fraction, a fraction truly is a division problem. A fraction truly is a division problem. So keep this in mind. A fraction, okay, is a division. A fraction is a division, or it means a division. More precisely describing it, a fraction means a division. And so a lot of times when you're having a division problem like this, say a p over q divided by, so a fraction or a rational expression divided by another fraction or a rational expression, this division also means, so in mathematical sense, we can write it as an equal sign. This division problem equals to the result of having a fraction over as a bigger fraction. So we having the following expression: a p over q all over a q over s. See, this is, if you're looking at that a little more closely, this is a fraction where numerator is a fraction and denominator is another fraction. All right, so that's another remark right there for everyone to understand. And so the equal signs right here means these two are the same. It turns out the same result like that. But so what's the consequence? What's the consequence of this remark I'm about to say right here? This problem 3 that we have done earlier, now let's ignore all of the work that was done. The same exact problem, it could have been worded, the same exact problem right here in problem 3, the original wording I was indicating is divide that into this. Okay, but the same exact problem, it could have been worded as following. Allow me to use a red ink right here, but it could have been worded as following. Simplify. We could have been instructed to simplify the following expression: a 3n squared over n squared minus 4n. And then that division, like I said, the division here means a fraction, or a fraction means a division. And so we can put this as in a division in a fraction setting. So the 3n squared over n squared minus 4n, I'm putting that over 9n squared. minus 45n, and then over n squared minus 7n plus 10. All right. See, you can look back at the work we've done earlier. Feel free to rewind the video lesson right here. But the work here was that we performing the divisions, and then in the end we simplified it. We simplified it all the way down to the most simplified form like that. So just like that, the instruction here gets straightforward into, hey, here you go. Here's a very large, complicated expression. But then we want to simplify that down. So now in our work right here, in the way how we're looking at that, see, I want you to understand that, and within the remark I've mentioned, the remark number 2 that I've mentioned, think of that as we have a fraction here divided by another fraction due to this long bar indicating it's a fraction between two little fractions. It's a fraction, it's a rational expression that contains where it has numerator being a small rational expression and denominator is another rational expression. And so when you're instructed to do something like this, your first responsibility is to understand this as a division. So it never hurts at all to rewrite this large expression into a division problem, and then we carry out the division process, just like how we've done that in the demonstration of the actual problem 3 earlier. All right, so now we're at example 2 right here. So after learning about the fundamental, the method right here, how we can divide any two rational expressions, and together with looking at some remarks right here, let's now drive that into an actual example right here so that we can see how we can follow the steps closely, how we can apply the steps closely into solving this problem. So the problem here is instructing us to divide this rational expression into this rational expression. So we have a division problem between the two rational expressions. Okay, so now step 1, as you have seen, and in my remark I've been mentioning, think of the division as a multiplication between, here's the first rational expression and this is the second one. And so I'm going to keep the first rational expression the same. So 2x squared plus 5x minus 12 over the x squared minus 16. I'm keeping that the same because think of a division as a multiplication between the first rational expression. There's nothing stated to modify the first rational expression, so we're leaving it here. A multiplication between the first rational expression and the reciprocal of the second one. So now this is how the reciprocal looks like. X squared minus 8x plus 16. And now we're looking at the 2x squared minus 13x plus 15. So now clearly the division problem was rewritten as a multiplication problem. And so now from this point on, our only responsibility is to carry on with this problem as a multiplication. And so it is important that we master the skill of how we can multiply any two rational expressions. It's simply just that. And so now, the next step into this, I'm going to go ahead and completely factor each of my numerators as well as each of my denominators. (2x minus 3 times in product with x plus 4. And then this denominator here will be factored into x minus 4 and x plus 4. And so once again, for anyone who's viewing this lesson feeling unsure about how I have gotten this factor form for that quadratic expression and then this factor form for this x squared minus 16, I highly recommend that you view the video lessons prior to this one where I was teaching about how you can factor these quadratic expressions. The next rational expression, and of course it's a multiplication, the numerator here becomes in factor form x minus 4 all square and all over. Now this denominator is factored into 2x minus 3 x minus 5. And so once again, everything has been taught in a lesson prior to this. And so now at this point right here, after completely factor all numerators and all denominators, now we're going to perform the usual multiplication. So the final numerator of our final rational expression has to be the product of all these factors being brought together. So now I'm going to have 2x minus 3 in product with x plus 4 in product with x minus 4 all squared. The final denominator is a product of all these factors being brought together. So x minus 4 times x plus 4 times 2x minus 3 and times x minus 5. So that's our final denominator here. And so with this final rational expression, now the next step here, and we have finished, think about the methods right here, then we have done up to step 3 right there. And so the last step here is to simplify. So now let's go ahead and recognize all of the common factors, to divide them out or to cancel them out. So I recognize there's a 2x minus 3 being common with that. I recognize a x plus 4 being common. I have recognized there's one factor of x minus 4 here, even though there are 2 here. So I'm going to cancel one of that away, and then cancel that, but leave behind an x minus 4. Okay. And so now the final expression here in the numerator, we have only just x minus 4. Now that 2 right here is the square of this. So after canceling out, it really just remains x minus 4. The writing is making it a little confusing right here. And then in the denominator, the only remaining factor is the x minus 5. So our final rational expression is x minus 4 all over x minus 5. And that is our final rational expression after dividing this rational expression by that other one.